So let's say, all right. So one of your example, this was number 14. It states that you were given a function was equal to the following series. If you have over one over one minus x, it's equal to the series of starting from n equals 0 to infinity of x to the n, right? And we want to use this, basically use it to find the MaClaurin series for x squared over 1 minus x. So this is what I did to figure it out. Basically, we know that, okay, this is what we should know. We know, okay, from the given, 1 over 1 minus x is equal to that series, x to the n, right? So term by term, this will be x to the 0 plus x to the first plus x squared plus yada, 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 all the way to x to the n, right? Now, essentially, the only difference between this function and the function that's given to us is the x squared, right? So if I manipulate this series to have an x squared in the numerator, then I just multiply it by x squared, right? If I basically take 1 over 1 minus x and I multiply this by x squared, then I have to also multiply the right-hand side of the equation by x squared, right? And if I'm multiplying the right-hand side by x squared, then I'm basically saying I have x squared times x to the n. Okay, so this will give us x squared on the top over 1 minus x. And in the for your MaClaurin series here, you have x squared times x to the n. Well, the bases are the same. You can add the exponents. This will give you x to the power of 2 plus n. And I think that would be your solution. I think that would be a legit solution to this problem. Only because, well, if you look at this side, right, this piece here, if I multiply all of that by, let's say, an x squared, then the first term will be x squared. The second term will be x cubed, right? This is equal to x squared plus x cubed plus x to the fourth, yada, 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 all the way to x to the power of 2 plus n. So it resembles what I wrote out on the bottom. So I think that's legit. Okay. It's just basically manipulating a little bit of algebra here. I don't think this one was a bad example.
Just use the photos.
No. Like there was one that was a little bit easier. I think that was problem number 11. It was easy at first to figure it out. And then for number 12 is where you had to like actually integrate it, right? So I'll show you another example. So for number 11, you were given e to the x is equal to the series or the sum of n equals 0 to infinity of x to the n times n divided by n factorial. And we want to use it, right? Use it to find the MaClaurin series for e to the power of negative x squared. So this is how I attacked this problem now. I said, okay, I wrote out the given series again. Right? I just rewrote it. And then wherever I see an x, right? Wherever I see this x, I'm going to replace that x with negative x squared. So this will give us e to the power of negative x squared equals the sum n equals 0 to infinity of negative x squared raised to the power of n, all divided by n factorial. Right, so basically I just replaced the x with negative x squared. And then I just took care of the algebra. So this piece here, you just got to be a little careful with. What you're going to get is the sum n equals 0 to infinity of, you could distribute the n inside the parentheses. Mm-hmm. So technically, the x squared is being multiplied by a negative 1. So you have negative 1 to the n power times x to the power of 2n divided by n factorial.
Simplify it.
This is fair enough. You don't got to simplify this further.
Gotcha.
This is good.
Like up to negative x squared to the n over n factorial, would that be wrong? Would that so break it down?
I think you will have to break it down a little bit more.
Gotcha.
You will have to break it down a little bit more because the next problem says that you want to use the MaClaurin series that you just found to find the integral of that MaClaurin series. Okay, so all I did here between the given line, right? Between the given and the next line, was that I replaced x with negative x squared. That's all I did. And now for your number 12, it says that, okay, oh, somebody asked. Oh, Preston, I simplified it because technically x squared is being multiplied by negative 1. So you apply one of the rules for exponents, algebra rules for exponents that allows us to take the n and distribute it to the negative 1 and the x squared. So you get negative 1 to the n. And then when you have x squared to the n power, you get to multiply the two exponents. So instead of saying x squared to the n, it's x to the power of 2n. Okay. So now that we got that taken care of, number 12 says to integrate the MaClaurin series for e to the power of negative x squared to find the MaClaurin of the integral e to the negative x squared dx. So basically what I did was the following. I start with where I left off within the previous problem. I say that, okay, I know that e to the negative x squared is equal to the sum n equals 0 to infinity of negative 1 to the n times x to the power of 2n, all divided by n factorial. So to find your MaClaurin now, for the integral part, you just got to integrate both sides, right? So we're going to get here a dx. Here we're going to integrate this in terms of dx. So when I integrate the right-hand side of our equation here, you're formulating a new sum, and this sum requires you to basically use the power rule for integrals, right? What you're going to get is still the sum from n equals 0 to infinity. Now remember, negative 1 to the n and n factorial, they're going to be constants. So they come along for the ride. So you got your negative 1 to the n on top. On the bottom, you're going to have your n factorial. But if you take the antiderivative of the x to the 2n, right? Using your power rule, you add 1 to the exponent and then divide by that sum. So what you're going to get is x to the power of 2n plus 1, and then you divide 2n plus 1 on the bottom, and that will be your solution. I think if I show you what this looks like term by term, I think it would justify, right? Here's my justification that this is legit. Okay, so originally in problem 11, it says e to the x is equal to the sum of n equals 0 to infinity of x to the n over n factorial, right? So if you want to write out the sum term by term, the first term would have been x to the 0 over 0 factorial, which, by the way, all of that is just 1, plus x to the first over 1 factorial, which is just x, or x to the first. Then you would have got x squared over 2 factorial, which is x squared over 2, plus yada yada yada, x to the n over n factorial. That's the pattern. Now, e to the power of negative x squared, well, the first term is still going to be 1, right? Because if n is 0, or x, yeah, if n was 0 for the sum, you're still going to get, from here, you're still going to get 1, right? Negative 1 to the 0 is 1, x to the 0 is 1, 1 factorial, 0 factorial is still 1. So the first term is 1. Now, if you want to do their second term, the second term would be a negative, because negative 1 to the first is negative. So you get negative 1 times x to the power of 2 times 1, which is just x squared, divided by 1 factorial. Right, so you would have got minus 1x squared, or just minus x squared over 1 factorial, which you can just leave as x, negative x squared. Your third term, if n was 2, well, then you have a positive x to the power of 2 times 2 is x to the fourth. So you've got x to the fourth over 2. All right. And then so forth, right? You would have followed the pattern. Again, the pattern says negative 1 to the n times x to the power of 2n over n factorial. Now, if I integrated just the first 3 terms, right, then when I plug in n, after I integrate it, when I plug in those n values into our solution for problem 12, we'll get those answers, right? The integral of e to the negative x squared dx. Well, what is the antiderivative of 1? X. What is the antiderivative of negative x squared?
Negative.
Yep, negative x to the third over, now be careful here, this one would have been over 3, so that's legit. Your next term would have been x to the what power? 5, but be careful because now you have to divide by 10, right? And then you continue on and on and on. Now, just to show you that this is legit, that was our solution to problem 12, right? If I plug in n equals 0, n equals 1, and n equals 2, I should get x, negative x to the third over 3, and x to the fifth over 10. So let's see. Well, when n is 0 in this sum, the first term, right? Well, negative 1 to the 0 is 1. You have x to the power of 1, because 2 times 0 is 0, so it's x, divided by 2 times 0 plus 1, which is still 1, and then 0 factorial is 1, right? So all of this is just 1 times x over 1 times 1. That's just x. So the first term is good. If you look at the second term, n equals 1 now, then you'll get -1 times x to the power of 2 times 1 plus 1, which is 3. So this is x to the third over 2 times 1 plus 1, which is 3. And then 1 factorial is just, what's up, man? 1 factorial is just still 1, right? So this is just now going to be negative x to the third over 3. I think we got that as a solution for the second term.
Yeah.
Yep. And then we do it for n equals 2. Well, that's going to be a positive 1 again. This will be now x to the fifth over 2 times 2 plus 1, which is 5, times 2 factorial, which is 2. So this is now x to the fifth over 10, which is exactly our third term.
Yeah.
So our justification works.
You don't have to do justification.
No, you don't have to do the justification. I'm just showing you. Yeah, why it worked. Okay. All good on these two problems?
Yeah.
All right. So I'm gonna do one more like this, and where I'm just manipulating the algebra. Okay. So the other one that was like this was number 13. So for number 13, it says sine of x is equal to the sum n equals 0 to infinity of -1 to the n times x to the power of 2n plus 1, all divided by 2n plus 1 factorial. So we want to use it, right? We're going to use it to find the MaClaurin series for 3 sine of x over 2. Again, all I think you have to do here is just manipulate the algebra. If you look at the sine function here, sine of x is being multiplied by 3, and then the x is being cut in half, right? X is being divided by 2. So there's two things I got to do, right? First, I just write out what's given to us. Just rewriting it doesn't hurt. I don't think, by the way, you have to memorize these formulas. I think these formulas will be given, like if it's on the exam.
Yeah.
I think it's given. It's just that you have to, manipulate the algebra. So first you multiply 3 on both sides. So you get 3 times sine of x equals 3 times the sum of n equals 0 of -1 to the n times x to the power of 2n plus 1. And all of that gets divided by 2n plus 1 factorial. Now, wherever you see an x, you got to cut x in half, right? There's 3, by the way, on the right-hand side of the equation. You could leave it alone. That could just stay outside. So you get 3 sine of x over 2. So now this is equal to 3, the sum, n equals 0 of -1 to the n. Now, x is being cut in half, like I said, so you have x over 2 raised to the power of 2n plus 1, all divided by 2n plus 1 factorial. Now, you could simplify this a little bit, right? You can simplify this. X over 2 is being raised to the power of 2n plus 1, which means that both numerator and denominator is raised to the power of 2n plus 1. So I'm just going to rewrite this right-hand side of the equation here. So you have -1 to the n. Now this would be x to the power of 2n plus 1 divided by 2 to the power of 2n plus 1, all divided by 2n plus 1 factorial. Now, technically speaking, this sorry, my bad. That was pretty thing. I'll use this one. I think this one's small. Yep, this here. So if you look at this 2 raised to the power of 2n plus 1, it's technically in the denominator of a fraction. And informally, what you can do is you can just bring this down into the denominator. So if you just shove this down here into the denominator, your final answer would be 3 times the sum n equals 0 of negative 1 to the n times x to the power of 2n plus 1, all divided by 2 times 2n plus 1 times 2n plus 1 factorial. And I think that's a legit answer. Any questions?
Mhm.